Okay, so conservation of energy. According to conservation of energy, although what we've been talking about so far, potential kinetic energy and the energy stored in a spring are considered as mechanical energy. So energy can never be created or destroyed. So it's something that is already present, okay? Can only be changed. So change from one form to another. So from one form to another. So it can be from gravitational energy, it will be converted to kinetic, or other forms of energy can also be converted to heat. Okay. So the energy lost by EP, so if we're talking about the mechanical energies, we talk about the potential and kinetic, is equal to the energy gained by the kinetic energy. So this is what happens if you have a falling object. So the total mechanical energy of the system is the sum of the potential and kinetic. So solving conservation problems. So identify and label the points of interest. So ABC, usually we just use ABC. You can also use point one, point two, or something like that. Any subscript. So point of interest. So A usually would be the starting point. B is the maybe the final point. If you have another point, you can use C. Okay. So set the total energy of A would be equivalent to total energy of B. So your starting equation will be total energy at A and the total energy at B. But it could be, again, your energy could consist of different forms. That's why you have their plus plus and then dot dot dot. Okay. So the total energy would be equivalent for the two different points. And then you need to solve for the unknown. So these are just the general way of solving conservation problems. So take an example here. A 25-kilogram rock sits at the edge of a 4.0 times 10 to the power of 1 meter high cliff. If the rock falls off the cliff to the ground, what would be its velocity as it hits the ground? Okay, so you're being asked there to use the energy equations because you can actually use also kinematic equation if everything is given or the right quantities are given. Okay, so you use the energy equations. So you have a rock. So maybe perhaps you have a cliff here. So the height of the cliff is 40 meters. Okay, 40 meters. Then it falls off the ground. So this is just the same thing as dropping. So it's just the same thing as being dropped. So we know that if it is dropped, velocity is equal to zero. Okay, so velocity is equal to zero. So therefore, initially, if this is your rock, so I call this one as my point A, and then the bottom would be called as point B. So velocity at A is equal to zero. Again, this particular statement here, the same thing as the object is being dropped. If the object is being dropped, again, velocity there is zero. Because you're just dropping it, you're not applying any uh, initial velocity. Okay, and then the height at A would be equivalent to 40 meters. Okay, so you use A as your initial position, and then, well, this drops, it reaches the ground. So they're asking for the velocity as it hits the ground. Okay, so this is the impact velocity, same thing as impact velocity. So don't think that the object already stops there. Well, it is the velocity upon it hits the ground. So that's a question mark. And you know that the height here would be, excuse me, height B is 0. Because again, you started, if this is, again, uh, the height of A would be 40, so it must be that the height at the bottom would be 0. Okay? So, I think, well, we're given the mass of the rock. So this is the mass, 5 kilograms. So we use the energy equation. Although I believe that with the givens that we have, we can actually use the kinematic equation. But again, we're being instructed to use the energy equation. So in this particular case, what would be the total energy? Well, it would be potential energy at A plus the kinetic energy at A, and that should be equivalent to the sum of the potential at B plus the kinetic at B. So you're just talking about here potential and gravitational potential energy and kinetic energy. So potential energy at A would be mg HA. So that's the expression for potential energy. Plus, what the expression for kinetic energy? Well, it's given as mv A squared divided by 2. So V sub A. Again, we're talking about point A here. And what would be the potential at B? That would be mgHB plus what would be the kinetic at B? Squared divided by 2. So if you can see here, every term of your expression, the two sides of the equation, will have the mass. So actually, you can see here that mass is irrelevant in this case because it's present in each of the terms. So I can just divide both sides by m, and that would cancel out. Okay, so the first expression would become GHA. And well, taking note that VA is equal to 0, so that means that this is also 0 here. So you don't have any initial, or the velocity at A is 0 because again, it's just falling, or well, same as dropping. So you don't have any initial velocity there. And then the height at B also, at the bottom of the ground, height is equal to 0. Okay, since you set at the point A as the 40 meters, so that means that the bottom part would be 0 because again, the distance between the 2 points A and B is 40 meters. So HB should be 0. Since that is 0, this particular term here is also 0. So practically in your equation, you have this expression. GHA is equal to V sub B squared divided by 2. And if you're solving, again, we want to solve for V sub B. So is it not that that is just equivalent to 2GHA is equal to vis-a-vis squared? Well, you have a square there, so you take the plus and the minus, okay? Square it. So that would give you vis-a-vis squared. Well, that would be plus and a minus, or a minus of 2 times 9.8 times 40. So if you're gonna solve for that in two significant digits, that would be plus and a minus 28 meters. However, since this is moving downwards, this should be negative 28 meters per second vis-a-vis. Or vis-a-vis is 28 meters per second down. If you can excuse me for a while. Was that hour falling or? Oh, okay. So the negative sign here indicates that it's B. It's down, not B, but it's downward. Okay. So since the question is velocity, you have to include the direction. Okay. So again, when you take the square root, remember that you have two roots, quadratic equation, plus and a minus. So I take the minus sign because I know that at the bottom, its direction is downward. Okay. Well, let's take example number 2. A car, mass of 750 kilograms, travels along a horizontal road. If the car goes up a 20-meter tall hill and has a velocity of 10 meters per second at the top of the hill, how fast was the car initially moving? So for this type of questions, again, since conservation of energy, you're just looking at two different points. Because actually along the way, at any point in time, like between A and B, let's say, go back to example number 1, the total energy as it moves down, as this route moves down, would just be equivalent. Okay, it would not change the total energy. So the total energy at A would just be equivalent to the total energy at, let's say, the middle part. The total energy would be the same. Although the potential energy decreases, but kinetic energy increases. But the decrease and the increase, if you take the sum, would just be equivalent to the energy at point A and the total energy at point B. So for this type of problem, or for conservation energy problems, since you know that at any point between 2 points or any 2 points along the way, total energy is just the same. Again, you're not talking about efficiency here, but the total energy. So what we can do is, again, it's better for us to make a diagram first. So, this is the hill, and then I have a car. Okay. Okay. So if this is my A, and then the top would be my B, so that means that, well, if I gonna set this one as the bottom part as the 0, so HA is equal to 0, and then initially moving, so that means that at point A, so that's a question mark, I don't know how fast it's moving, but it moves in such a way that it reaches the top, okay? And then at this top portion, so that means that your car would be here already. The height of that hill is 20.0 meters. So that means that HB, since I set my A as 0, so this should be 20 meters. And then given that at the top of the hill, its velocity or its uh, speed is 10.0 meters per second. Okay, so yeah, so I have just 2 points here, and then I want to get my V sub A. So how fast is this particular car initially moving? So this is for the fact that friction is negligible, okay? Because if there's friction, there must be a friction component in your total energy, uh, the energy equation that you will be having here. So this is for a particular case that there's no friction. So you disregard friction. So again, two energies would be at A, and that would be potential and kinetic. So E sub PA and this is sub KA. And then this should be potential at B plus the kinetic at B. So again, there's no friction here. That's why there's no friction component in the total energy computation. So what would be the potential energy at A? Well, it's given by mgHA. So subscript is A, height at A, plus kinetic energy is mv sub A squared divided by 2. And then potential at B would be mgHB plus this would be mv sub B squared divided by 2. Okay. So if you can see here, well, mass is again present in each of the term. So I can just get rid of m. And then looking at the expression HA, so if you can see here, HA is equal to 0. So this particular term should be equal to 0. Well, I can no longer make my VA over 2 here is equal to 0 because, again, I know that it should be moving. So that would remain. HB has a particular value also, as well as V sub B. So actually, it's only the first term of the left-hand side of the equation that I can get rid of, because again, that's equivalent to 0. So this is V sub A squared over 2 equals to GHB plus V sub B squared over 2. So if you can see, I can solve for, well, everything is given except for V sub A. Okay. So if I gonna somehow solve for that, uh, well, this would be VA squared over 2, and then GH is 9.8 times the HB, which is 20, plus B sub B is 10. But remember that this is squared, so don't forget that. Usually the particular quantity is being forgotten. So you'll have B sub A squared divided by 2 is equal to, so this is 196 plus 100 divided by 2 is 50. And then solving for V sub A, so it's multiplied by 2. So that means this whole two terms here should be multiplied by 2. So be careful if you're gonna do this one. Remember that you're gonna multiply these two terms here by 2 as well. Not only the 196, but it should be 2 times the quantity 196 plus 50. So that gives me 492. And again, taking the square root of both sides, well, that would be v sub a. Well, this would be moving to the right, so I take the positive sign. So that would give me 22.2 meters per second, or again, positive means that would be moving to the right. Okay. So that means that if you can see, the initial velocity at the bottom should be bigger because some of that energy is being used up, convert to potential energy because it gains potential energy. So it should be slowing down at the top. Because again, some of the kinetic energy, so the difference here is around 12 meters per second, right? So that loss of kinetic energy is being converted to your potential energy. You have a gain in potential energy. Remember that at point A, potential energy is 0. But at point B, you gain a, a gravitational potential energy because of the gain in height. Okay, so you gain a height of 20 meters. So actually, the slowing down, the kinetic energy at the bottom, some of it is converted to uh, potential energy. Example number 3, you have here, a polygon uses a spring, 35 newtons per meter, to fire small marbles. Mass is 50 grams. How fast will the gun fire a marble if the spring is compressed at 7.5 centimeters? Okay, so in this particular case, your motion is should be taken as just in the horizontal direction. So, or in a more complicated question, is perhaps you're gonna mix it with something that is being fired upward. So because if you have upward there, that means that you are gaining some height. Okay, if you're gaining some height, remember that you'll gain potential energy, gravitational potential energy. But if you have a spring, you have another form of potential energy, right? We call it as the spring potential energy. So in this particular case, if this happens horizontally, so that means that the movement of this particular marble is just horizontally. So that means that just moves from from a toy gun. Uh, toy gun would be that one there, and then you have a spring inside. Okay, then you have this. So this would be the initial state. So I call this one at A. And then at B, this particular marble now moves. Okay, so it's moving at a certain velocity. So if you're gonna look at this one here, V sub A is 0. It's not moving. And then V sub B would be the question mark. I don't know that. So for sure it's moving. So how fast will the marble fire? The marble is the spring is compressed. So uh, actually this is the marble when it leaves the spring. So that would be its velocity. What would be its velocity once it leaves? Okay, when it leaves that particular spring. So again, in this case, HA is just equivalent to HB. So therefore, you don't have any gain in potential energy here. Okay, so potential energy or gravitational potential energy here is not taken into account. So because you can set that one as zero because there's no difference. So you can set that one as zero because if you can see there's no vertical distance. So that would be zero. So that means the potential gravitational potential at A is just is equal to zero as well as the potential energy at B. So it's just zero. Set that one to zero. Because anyway, again, there's no change in height. So if I'm gonna go back to my conservation of energy, I'm just now talking about the spring energy or the elastic potential energy plus the kinetic energy at A is equivalent to the elastic potential energy at B plus kinetic energy at B. So again, I don't have any potential or gravitational potential energy here because there's no difference in the height between A and B. So I can just set that one to zero. So both would be zero, so therefore potential energy, gravitational potential energy is zero. And now for the spring, elastic potential energy is 1/2 kxa squared. So that's the formula for gravitational potential, no, not gravitational, but elastic potential energy. Plus 1/2 mv sub a squared is equal to, again, the elastic potential energy at B would be 1/2 kx b squared, okay, plus kinetic energy would be mv sub b squared, okay. So if you can see all of the terms again, so this is how equation works. If every of the equation contains a particular number that is the same for everything, you can cancel that one out. So you can cancel out the 1/2 here because, again, because it is present in every term. So it's present in every term. Therefore, that can be canceled out. So the initial velocity at A, this doesn't move, it's not moving, but you have a particular displacement with that. So this could also be zero. Because if this is zero, so therefore this particular term is zero. Okay? And is it not at B? At B, the x, the displacement from its equilibrium position is actually zero because it's no longer compressed. Okay? So xb should be equivalent to zero. But on xa, you have, again, at position A, you try to compress the uh, the spring. So XA should be equivalent to 7.5. Or again, for K, we use Newton per meter. So this tells you that the distance should be in meter. So therefore, I need to convert that one to meter to be consistent with my units. So all distances must be in terms of meter. So that is why I'm going to convert this one to meter. So this is now 0.075 meter. Again, XA is equivalent to 0.075 meter because you're compressing. Remember that by definition, that's coming from the Hooke's law. The X there pertains to the compression or the expansion, or if you're stretching it from the equilibrium position or compressing it from the equilibrium position. So that's how you measure your X in the uh, Hooke's law equation. So in this case, you are compressing it by that, so that should be your XA. But in XB, again, it's already uncoiled, so therefore there's no more displacement. So XB is equal to 0. So if that is equal to 0, that means that the first term of the right-hand side, since this is 0, so this would be 0 also. So basically, you can have the expression of K XA squared is equal to MV sub V squared of no more over 2. So if you can see here, you cannot disregard the mass quantity. You can no longer disregard that one because the other side doesn't contain mass. So therefore, M should be present there. So you should be, well, substituting. K is 35 multiplied by the value of A, that's 0.075 squared. So remember that XA, it's to the power of 2. So you're trying to square that particular number. And then mass is, well, 50 grams. But remember, Newton is a derived unit that has a quantity of kilogram. So therefore, that means that mass also should be written in kilogram. So this should be converting this one. This is 0.05 multiplied vis-a-vis squared. Okay. So you'll get vis-a-vis would be the square root of 35 times 0.075 squared divided by point. So just be careful when you try to do this on your calculator. Remember that everything is being placed inside the square root symbol. Okay. Well, it says how fast. So this is just the speed. Okay. So no need to indicate the direction. So vis-a-vis would be equivalent to 2.0 meters per second. So I no longer use the plus or minus sign here, because anyway, I know that I'm just solving for the magnitude of the velocity or just the speed. So it should be moving 2 meters per second. So that, again, horizontally, although it's fired at a certain height, well, we know that it becomes a projectile motion. So again, this is the velocity once it leaves that particular spring. Okay, so that would be 2 meters per second. Okay. So let's try to, yeah, example number 4 is just a comparison. Again, the conservation of energy just gives you another tool in solving these kinematic quantities, because velocity and speed, or the distance, the time, are considered kinematic quantities, right? We talk about these quantities in unit 2. But knowing the energy implication, conservation of energy, is another way of solving them. But with the right particular quantities given, we can also solve them using the kinematic equation. Okay. So let's say example number 4 here. Well, the path of an object follows as its raised or lower does not affect its final potential energy. Okay, and let's take this example here. A 1 kilogram ball is dropped from a height of 2.5 meters. Again, it's dropped. So here in the air, it's dropped. So that means that we mean that the velocity is zero in that particular case from a height of 2.5 meters. So for letter A, we will try to use the conservation of energy to determine uh, its velocity when it hits the ground. So its velocity. So again, if it's asking for a vector quantity, your final answer should be both magnitude and direction. That's a vector quantity. So magnitude and direction. Okay, because velocity, well, if it's asking for the speed, impact speed, well, you can just consider the magnitude it hits the ground. Okay, so for letter A, we're going to use the conservation of energy uh, principle. So again, in this particular case, you have just an object, so being dropped. So this is my point A, moves at the hits the ground. That would be my point B. So the height of this is 2.5 meters. Okay, but initially, since it is being dropped, that should be equal to zero. Vis-a-vis here is the main question. Okay, so for letter A, I'll be using the conservation of energy. So again, in this case, yeah, maybe in physics 12, you'll be becomes harder because you'll be dealing with a frictional force. But in our case, we try to assume that there's no friction here. Friction is not a factor. So therefore, we're just talking about the potential, gravitational potential energy and the kinetic energy at these 2 points. So potential at A plus the kinetic at A would be equivalent to the sum of the potential at B plus the kinetic at B, of the sum. So again, A in this particular case is a particular height. So HA is equal to 2.5 meters. HB would be 0 meter because I set my HA as the 2.5. Therefore, at the bottom, it becomes 0. So this would be MGHA plus, this is MVA squared over 2. AP sub B would be MGHB plus MV sub B squared over 2. And as well as before, mass is not a factor. M is present in every of the term here. So therefore, I can just disregard that. As well as VA is 0. So if this is 0 here, this particular term is equal to 0. HB is also 0. So that means that this first term is equal to 0. So essentially, you will get GHA is equal to V sub V squared over 2. Or that is just 2GHA is equal to V sub V squared. So taking the square root of both sides, again, plus and a minus. So in our convention, it's moving downward. We just use the negative sign for that. So that means that this is negative something. So I'll be using the negative of 2 times 9.8 times 2.5 is equal to V sub V. The square root of this. So V sub V is 7.0 meters per second down. Okay, so that would be my answer. The magnitude is 7 meters per second. Its direction is downward. Okay, so now I use the kinematic equation. Using kinematics determines velocity when it hits the ground. Kinematics. We know that, well, for any falling object, its acceleration is constant, and that's equivalent to negative 9.8 meters per second squared. So we know that the velocity at A is equal to uh, 0. So initial would be 0. And then acceleration is negative 9.8 meters per second squared. So again, this is uh, on the coordinate system upon which downward uh, would be would be negative. And what else? We're given D, but what would be the displacement downward? Well, again, if we're gonna use negative 9.8, that means that our starting position would be at A, and then downward of A, if this is your zero mark, 0 meter, so that would be your initial position. If you're gonna set that one again, in our case, this is 0, so upward is positive, downward of 0 is negative. So therefore, at the bottom, that should be negative 2.5 meters. So therefore, the displacement here would be negative 2.5 meters. Okay. So again, since I'm using the coordinate system of downward as the negative, okay, in this case, downward direction is negative. And I'm solving for vis-a-vis, that would be my question mark. Well, for the equation that I'll be using, if you can check, well, you have 1, 2, and 3. So this is good enough because for the kinematic equations, again, if you're given at least 3, that would be enough to solve for the other 2 quantities that you need to solve. Okay. So again, you can actually solve also the time here as well as the final velocity or the velocity at B. So choosing the correct equation, I got this equation here, vis-a-vis squared is equal to vis-a-vis A squared plus 2AD. So this is just vis-a-vis the square root of, again, I have a plus and a minus. That would be 0 plus 2 times negative 9.8 times the height of, or the displacement in this case, negative 2.5. So if you can see the negative signs there, that's actually just for consistency of the calculation, although it doesn't affect the value. Well, strictly speaking, it can affect if you use positive 2.5 here, the square root of a negative is undefined, right? So that should give you an idea that maybe perhaps you messed up with the coordinate system that you use. Okay, because if I use downward as positive, that means that the acceleration is also positive 9.8. But since again I use this particular coordinate system, the middle part starting point is 0, so going up is positive, going downward is negative. So I use that particular coordinate system. So therefore, yeah, I need to be consistent with that. So if you can see here, well, this should give you, again, it's going downward. So that means that I'll be using the negative 7.0 meters per second, or final answer should be 7.0 meters per second, then the direction is down. So if you can see, you'll get the same answer, okay? So same answer as it should be. Should get the same answer. So again, the energy equation just gives you another way of solving things. Just like what I mentioned about work, the work energy theorem, So you use dynamics there, related to dynamics and related to kinematics. So yeah, if you can see, you have the same answer. Okay. Okay, let's take example number 5. A toy car with a mass of 100 grams is moving along a track with a velocity of 10 meters per second when it runs into a spring. How far must the spring compress to bring the car to a stop? Okay, so I'm gonna start my solution here with a diagram. So you have a car moving, uh, okay, moves in that direction, and then I have a spring. So encounter the spring, maybe, okay. So just before it hits, okay. So just before it hits the this particular spring, it's moving at. So that would be, well, again, if I can call this one as a VA, it's 10 meters per second. And if you can see your XA, again, XA pertains to the displacement of your spring. Well, if you can see, there's no displacement there. So therefore, that should also be 0. Okay. And then we're given that case 15 Newton per meter. So that's a spring constant. And at point B, well, it should be that it hits. So at point B, your drawing or your diagram would be something like the car hitting now the spring, but this is now being compressed. Okay, this is now being compressed at a certain uh, XB. So actually, that's the main question there. Spring compresses to bring it to a stop. So that means that vis-a-vis, since the word stop, so vis-a-vis is equal to 0. So this should be 0. But the main question is what would be the displacement? Okay, so that would be your XG. So actually, you can use dynamics, the Newton's laws of motion here, combination with kinematic equation to solve for that. But I think it would be simpler if we use the conservation of energy. Okay, so I just want to take note that the mass here is given in grams, so therefore, well, in kilogram that should be 0.1. Okay, so that would be 0.1000 kilogram. Okay, so again, I just want to be consistent with my units. So remember that K is Newton, and Newton is kilogram meters per second squared. So that means the mass should be in kilogram, distance must be in meter, as well as the time should be in second. So that's my basis of my conversion. Well, this is good here because this is already meters per second, so I don't need to do anything with that. Okay, so I go back to my conservation of energy. So the energy, the total energy at A should be equivalent to the total energy at B. So total energy here should be equivalent. Okay, so that's my starting equation. The total energy. Well, what are the energy that it's talking about? Well, this is just moving horizontally. Again, a more complicated thing about this one is that if you have somehow this is moving upward, but since again it's just moving horizontally, so you don't have any gravitational potential energy. Okay, so you can again, just like before, you can set the potential energy at 0, gravitational potential energy. What you have would be, since you have spring here, there should be spring elastic potential energy. So that would be elastic potential at A plus, again, you don't have any gravitational potential energy, but you have kinetic energy at A, should be equivalent to the sum of the elastic potential at B plus the kinetic energy at B. Okay? So now I just have to expand. What would be the expression for the elastic uh, potential energy? Well, it's given by 1/2 kxa squared. So just don't forget that in your elastic potential energy equation, you have x to the power of 2 plus this is mv squared of a over 2 or 1/2 is equal to 1/2 kxb squared plus mv sub b squared over 2. So if you can see here, everything has 1/2, so I can cancel that 1/2. So express it in every term. So as long as you have a number or a quantity that is present in every term, you can cancel that one out. Okay? So I cannot get rid of k here and m because, well, k and m is not present in every term. It should be present in every term. So going back to the given here, I've given that xa is 0. So if it is 0, so this term is also 0. How about v sub a? Well, it's not 0, so therefore that particular term holds. xb, kxb, well, that is not equal to 0 also because there's a compression. So there must be displacement of my spring. So that is non-zero. The next term would be v sub b. Well, it stops. So that means that the velocity when it made the compression is equal to 0. It stops. So if that is 0, if this is 0, that means that this is 0 here. Okay? So that simplifies our equation to mv sub a squared is equal to kx sub b squared. And this is good because the only unknown here is actually the compression. Okay. So again, we're gonna write v sub a squared is equal to kx b squared. So if you can see it, xb is just the square root of mv sub a squared over 2 or over k. So remember that I'm just asking for the compression. So that's already the displacement. So in a way, I'm just solving for its distance from the equilibrium position. So that should give me, well, I'm going to substitute that 0.1 multiplied by 10 squared divided by 15. So taking the square root, so maybe you can check if you get the same thing. The answer is 0.82 meters. So the spring must be, yeah, must be displacing at the particular value. So it's kind of straightforward if you use the energy equation. But if you use dynamic Newton's laws here, there should be two-step process. You're gonna use Newton's law to get the acceleration, and then if you get the acceleration, now you can now use the kinematic equation to solve for this displacement. Okay, so in a way, this becomes a shortcut because if you're gonna use again, yeah, if you want to try it out, like using the Newton's laws of motion as well as the kinematic equation to solve for xb. You can actually also that. Maybe if you want to challenge yourself. But in a way, with this knowing that the energy is conserved, so that means that we're not talking. So there must be no friction also in this case. So if we're gonna use the dynamics equation as well as kinematic equation, especially in the dynamics equation for the Newton's laws, so we'll just be talking about uh, in this case the force exerted by the spring. There should be no friction involved. Okay, because in the energy equation also we try to disregard friction. Okay, so that would become more complicated if there's friction involved, as well if you can add more if this particular card is moving upward, because you cannot set your gravitational potential energy in the particular case as zero. And it's not as simple as, again, you have to take into account in your energy equation here if you have friction. Okay, so actually you have an additional term in your right hand side of the equation for the friction part, but we will not touch about that. So last example. So I'm just gonna go through the last example, number 6. We'll no longer do the pendulum or part. So Mara is visiting Land of Play for the roller coasters. So a 2 times 10 to the power of 2 kilogram roller coaster starts from rest. Its velocity, determine its velocity at B, C, and D. Okay, so we're trying to solve what would be the velocity. Yeah, this would be V sub B, question mark, and this would be V sub D. No, it's D. That's also question mark, and as well as this point here, what would be V sub C? That's a question mark. Okay. Uh, most roller coasters actually use this concept. Uh, Maybe it uses electrical energy to bring it upward, but once it is up, that particular roller coaster is just being dropped at a certain height. So there's no motor in the wheels of your roller coaster. So that's the basic concept behind a roller coaster. It just uses the potential energy that it gains when it is being released from a certain height. Okay, so start from rest. So that means V sub A is equal to 0 here. And let's say, for example, uh, the height would be based from the ground. So that means that this is 0 meter. So that means that HA is 30 meters. That means that HB is 15 meters. So I set my ground as 0. So the height would be measured from there. So the ground is again the 0 meter. So that means that HB is 15 meters. HC is 0, as well as HD is 5 meters. Okay. So again, I would assume that there's no friction in this particular case. So at any point, the total energy would be the same. Okay. Again, total energy would be the same at any point. At any point is the same. Again, the total energy, I'm talking about the total energy, is the same. So that means that the sum of the, well, you're just talking about potential and kinetic in this particular case. So the sum of the potential at A and the kinetic at A would just be the same thing as the sum of the potential at B plus the kinetic at B, as well as the kinetic plus the potential at A would just be the same thing as the kinetic and the potential at C, and so on and so forth. So that's the meaning of that. So total energy at any point would be the same. So the total energy, again, I'm talking about the total energy. There could be some difference in uh, the velocity because at A, it's quite obvious that it's zero at A. Okay. So therefore, say, uh, point A and B. So A to B. So A to B. So I start with A to B. So point A and point B. I'll be looking at that. So at point A, you have again potential energy at A plus the kinetic at A would just be equivalent to the sum. Again, sum of the potential at B plus the kinetic at B. So this would be mgha plus mv sub a squared over 2 is equal to mghb plus mv squared b divided by 2. So I can somehow, since v sub a is 0, so that means that this is 0 here, as well as I can cancel out my m, because m is present in every term, okay? And if you can see here, v sub b is not 0 because I can expect that there should be some value in that particular case, okay? So I cannot set that one as 0. I cannot assume that it is equal to 0. What I'm sure of is just the velocity at A, or the speed at A is 0. So therefore, the kinetic energy at A is 0. HB is also has a particular height, so therefore, I cannot just say that its potential energy is 0. So you have GHA, then GHB plus. Okay, in this particular case, don't be tempted to cancel out G because G is not present in my second term here in my right-hand side of the equation. So I cannot cancel that one out. But I can solve. So this would be GHA. So if I'm gonna transpose this one to the other side, that would be GHB is equal to V sub B squared over 2. So solving for V sub B, this should be the square root of 2 times GHA minus GHB. Okay. So 2 times that, the difference of GHA minus GHB. And if I'm gonna substitute the values, kindly check if I'm gonna substitute 2 times 9.8 multiplied by HA. So HA is 30 minus 9.8 times HB of 15. We have several brackets here. Just be careful because you need to multiply 9.8 times 30 here before you subtract the product of 9.8 times 15, and then after which you're gonna multiply it by 2, and then you take the square root. So that should be equivalent to 17 meters per second. Okay, so 17 meters per second. So that would be the velocity here. So it could be moving, well, in that direction. But let's just say instead of velocity, we'll just use the speed. So we're just getting the magnitudes, okay? The magnitudes at different points. So at C, so now we are talking about point C. So I think for simplicity, because if you can see at point A, we can actually disregard 1. Kinetic energy is equal to 0. So I'm just going to use that one. I'm not saying that you cannot use B to C also, because actually you can also do that. Like comparing the total energy at B should just be equivalent to the total energy at C. But just for simple computation, I'll just use A to C, okay? Because at any 2 points, again, at any point, the total energy is just the same. Again, total energy would just be the same. However, I just use A as my starting point because I know that based on the first solution that I got here, kinetic energy at A is 0. So therefore, I can eliminate one term. So this should be potential at A plus kinetic at A is equal to potential at C plus kinetic at C. Again, I know already from the previous one that kinetic at A is 0. So I'm just going to expand this mgha is equal to mghc plus mv sub c squared over 2. So at point C, hc is 0, so therefore this is 0. As well as I can again disregard m. So if you can see, it becomes simpler. This would be 2GHA is equal to VC squared. So if I gotta take the square root of that, again, I'm just solving for the magnitude. So 2 times 9.8 times HA. HA is 30 is equal to VC. So VC is equal to, if I'm gonna take the square root of that, that should give me 24. So 24, that would be 24 meters per second, okay? So actually at point C, all of your potential, if you can see, all of your potential energy is converted to kinetic. This is actually the maximum speed that your roller coaster can gain. So how about D? So again, instead of using, I can also use C to D, but since I already set myself that A is kinetic at A is 0, so I'll just be looking at point A and point B. So total energy would be potential plus the kinetic at A. Again, looking at from A to D. So therefore, potential at D plus kinetic at D. So automatically from the previous example, this is 0. Again, kinetic at A is 0. So I'm just talking about mgha is equal to potential at D would be mghd. Well, if you're going to look at that one, HD has a particular height. So therefore, that should not be equal to 0. And this is mv squared d over 2. So mass is present in every of the terms. I can cancel out m. And this is just mgha minus, no, not m, but ghd is equal to v sub d squared over 2. Or you have the square root of 2 GHA minus GHD is equal to VD. So this would be VD. This would be the square root of 2 times 9.8 multiplied by HA. HA is 30 subtracted with 9.8 multiplied by the HD is 5 meters. So VD is equal to 22 meters per second. So if you can see, the maximum speed is at C, because that is where all of your potential energy is converted to kinetic. But at D, some of your kinetic energy is converted back to potential. So that's why you have a lesser speed, okay? And the very least is at point B. So the speed now is already 17 meters per second, because if you're gonna look at the height is also bigger. H is bigger, so that means that the potential energy is also bigger. Okay, so that ends our discussion for.
Mr. Villarin,
Yes.
would you mind just showing the second half that you did just off the paper just for a little bit?
Which one?
Yeah, like that. Perfect.
Okay.
Thank you.
You're welcome. So yeah, that's same concept with the third page, but we're just gonna stop with that. So